Okay, so now let us look at the closeness centrality. So the closeness centrality is a measure of um, how close is a vertex to the rest of the vertices in the graph. So if you look at this graph, so the first thing we have to compute is the distance matrix. So the distance matrix captures the distance from a vertex to every other vertex in this graph. And how we get that distance is basically run the breadth first search algorithm and find the level numbers of the vertices starting from the root vertex. So here we have 8 vertices, so we have to run breadth first search starting from each vertex, and that will give the distance from that vertex to the rest of the vertices. So like in this case for vertex 1, the distance from 1 to itself is 0. That's a level number. Now 1 to 2, so that's like distance 1. So level numbers captures the shortest path. So 1 to 2 is distance 1, 1 to 3 is also 1, 1 to 4 is 1, 1 to 5 is 1. And 1 to 6 is 2 edges, so level 2. Then 1 to 7 is like 3 edges, 1 to 8 is 2 edges. So the distance matrix gives you the shortest path from each vertex to every other vertex. So for vertex 2, it is distance 1 to 1, to itself is 0, to 3 it is 2, to 4 it is also 2, to 5 it is 2, to 6 it is 1, to 7 it is 2, to 8 it is 1. Okay, so once you get the distance matrix, you find the sum of the distances. So 1 plus 1 plus 1 plus 1 plus 2 plus 3 plus 2, that is 11. Similarly for 2 it is 11 and so on. Now find the inverse of this sum. So 1 divided by 11 is 0.1909. 1 divided by 11 is 0.10909. 1 divided by 17 is 0.0588. So the closeness is the inverse of the sum. And so why we take the inverse? Because we want to find the closer vertex, so we would really prefer smaller value for the sum. Okay, now we want to maintain the convention that larger the centrality value, the higher rank is the vertex, the better the vertex. So that's why we take the inverse. So when we take the inverse of a smaller value, it's going to get larger. For example, compare 21 and 11. Inverse of 11 is 0.0909, whereas inverse of 21 is 0.0476. So that means this vertex has a larger or a better vertex in terms of closeness centrality value. So it has a larger closeness centrality, even though its sum of the distances is lower, the inverse of it is going to get larger. Okay. Now the closeness centrality also has this problem of, since the sum is going to be an integer, it is possible that there could be multiple vertices having the same smaller value. Like in this case, both 1 and 2 have a smaller value for the sum of the distances. So they have the same closeness centrality. Now if you look at the time complexity of computing closeness centrality, you have to run breadth first search for each vertex. So breadth first search run for a particular vertex would take v plus e time, and multiplied by the number of vertices is going to be ve plus v square. Now the eigenvector centrality is going to take v cube time, because you multiply adjacency matrix with the column vector, that's going to be v square multiplications like the degree centrality, and you go through how many iterations. At the worst case, we'll go through the number of iterations corresponding to the number of vertices. So the 8 vertices, at the worst case, again you will go through 8 iterations. Okay, so that's something you have to know. So the number of iterations correspond to the at most the number of vertices. So that's why it's v squared times v, which is v cube. So it's a v cube complexity metric, whereas the closeness is ve plus v squared. That's the complexity of closeness. So both are kind of time consuming metrics compared to the degree centrality. Okay, so degree centrality is basically the most lightweight metric. Okay, stop with this.